Dear students, now we are going to an important theorem. So the theorem states that if I is a part of R, I is a part of R, I being an integral, and f is defined from I to R, where f is an increasing function. F is an increasing function. Let C fall in I. C fall in I, and if I equals closed interval AB, then this C always lies in between this A and B. That is, C is not an endpoint of I. Here C is not an endpoint of I, and f is an increasing function from I to R, then limit x tends to C plus f of x. Limit x tends to C plus f of x, or f equals equals infimum set of all f of x, where x fall in I with x greater than C. This is an important theorem. In previous class we already proved limit x tends to, under these conditions, limit x tends to C minus f equals supremum f of x for all x fall in I with x less than C. Here we prove the second result. If f from I to R is an increasing function, where I is a subset of R, C is nothing but an endpoint of this closed interval I, then limit x tends to C plus f of x is infimum of f of x with x fall in I such that x greater than C. How to prove this one? So the proof is in this way. You can choose let B equals set of all f of x with x fall in I such that x greater than C, where C lies in between A and B. What is f? It is given f is an increasing function. Since f is an increasing function, x greater than C, then that should imply f of x greater than or equals f of C, or f of x greater than f of C. Why? Because f is increasing function. Okay, so f of x greater than f of C for all x fall in I with x greater than C. This is written as f of x greater than f of C for all x fall in I with x greater than C. That means the set B is bounded below by which one? By f of C. That means B is bounded below. B is bounded below by f of C. Since B is bounded below, then infimum of B exists. Infimum B exists. Let it be L dash. Let L dash be the infimum of B. But we know that epsilon is positive. Since epsilon positive and L dash be the greatest lower bound of B, then L dash plus epsilon is not a lower bound of B, which is not a lower bound. Since epsilon is positive, L dash plus epsilon is not a lower bound of B. Since L dash plus epsilon is not a lower bound of B, then there exists some y fall in B. What is B? Set of all f of x with x fall in I with x greater than C. So y fall in B such that y greater than C. Why? Because of the construction of B. Y fall in B with a y greater than C, then such that this L dash greater than f of y, that should greater than L dash plus epsilon. L dash greater than f of y greater than L dash plus epsilon. So put a delta delta equals y minus c. In previous case we put a delta equals c minus y. Here put a delta equals y minus c. Choose set the following I. Choose set the following I such that c less than set less than y. What is I? I is closed interval AB. And what is C? C is not an endpoint of I, means C lies in between this endpoints A and B. So you can choose set the following I with a C less than Z less than Y. Now C less than Z less than Y, and what is F? F is an increasing function. So F is increasing, that means, this means F of C less than or equals F of Z less than or equals F of Y. Since C less than Z less than Y, then F is an increasing function, then F of C less than or equals F of Z less than or equals F of Y. Okay. Now, F of C less than or equals F of Z less than or equals Y, and L dash greater than F of Y greater than L dash plus epsilon. So that means that combinedly gives L dash less than F of Z, but this F of Z less than or equals F of Y, but this F of Y is greater than L dash plus epsilon. Therefore, L dash less than F of Z less than L dash plus epsilon. This means L dash minus epsilon less than F of Z less than L dash plus epsilon. This means F of Z falling where F of Z falling open interval L dash minus epsilon L dash plus epsilon. Okay. So that means, that is, when Z lies in between where C and Y, that is for C less than Z less than Y, that is unset the following I, then F of Z falling open interval L dash minus epsilon and L dash plus L dash minus epsilon L dash plus epsilon. Agree. But what is Y and Z? Come to this one. Z less than Y. Z less than Y means Y greater than Z. Okay. Y greater than Z. Y greater than Z means so what is C minus Y? C minus Y greater than C minus Z. But what is delta? We choose delta equals Y minus. This is our choice. So C minus Y delta equals Y minus C, and Y greater than Z implies Y minus C greater than Z minus C. Okay, but Y minus C is delta. That means delta greater than Z minus C. That means C plus delta. C plus delta greater than Z. C plus delta greater than Z. That means Z less than C plus delta. Y greater than Z. Y greater than Z means Y minus C greater than Z minus C. So that implies Z less than C plus delta. So again, come to this result. For set the following I, with C, we know that C less than Z from here, but Z less than C plus delta. So it is set the following I with a set lies in between C and C plus delta. What is F such? F set lies in between where L dash minus epsilon and the L dash plus epsilon. Okay. So this result comprises to this one. That is for set the following I with a set lies in between C and C plus delta. The form set the following L dash minus epsilon open interval L dash minus epsilon L dash plus epsilon. Set the lies in between C and C plus delta means set the following where open interval C and C plus delta. Implies F of set the following where F of set the following open interval L dash minus epsilon L dash plus epsilon. Clear? So set following C and C plus delta, set following open interval C and C plus delta, and f of set following L minus epsilon open interval L dash minus epsilon L dash plus epsilon. So that means set following open interval C plus delta means it is limit term x tends to C plus f of x equals which one? Equals L dash. Okay. What is this L dash? L dash is infimum of B. And what is B? B is setting as B is a set of all f of x for all x following I with a x greater than C. So this is what we require here. So this is the result. So this result shows that means if f is an increasing function, if f is from I to R where I is an interval and f is an increasing function, f is an increasing function and C is not an endpoint of this I, means C lies in between this A and B, C is not an endpoint, then there are two results, that is limit x tends to C minus f equals supremum f of x for all x following I with x less than C, and limit x tends to C plus f equals infimum f of x for all x following I with x greater than C. So the result states these two important statements, these two important conditions. That is, when f is an increasing function and I is an interval, C is not an endpoint of that interval, then limit x tends to C plus f. Limit x tends to C minus f is f of C minus. That is, f of C minus is nothing but supremum f of x for all x following I with x less than C. And limit x tends to C plus f, that is f of C plus. F of C plus is infimum f of x for all x following I with x greater than C. So this is the two results. If f is an increasing function, then f of C plus and f of C minus are defined in terms of their supremum and infimum of the given function, given increasing function f. Agree. So now there is an equivalent result, that is when f is continuous at C, then limit x tends to C minus f of x is same as limit x tends to C plus f, and its supremum value means like this. So these are the three equivalence results.